So you really want to learn the full, true solution to the general Quintic equation. You really want to, you're really that curious to want to go into the deepest, darkest pits of mystery and pain and suffering, to be honest. I know I said that I wasn't going to make this video in the quartic one, but my plunge into the rabbit hole of research articles and stuff on this sort of ended last winter break, where I found basically one way to get a solution. There's multiple different ways actually, but this was one way that I decently understood, the way to basically transform, get the solution to the reduced equation and then go back basically. It is still wildly inefficient and not practical at all, even to use with computers like with Wolfram Mathematica and that sort of thing. I did some experience with that. But yeah, if you're interested, I'm going to go into a general overview with this. It's going to be, again, basically transformations, a lot more of them compared to the cubic and the quartic before. Then we're going to get a clever series solution, and then also use some light analytic continuation of this to make it basically converge for basically any coefficients that you'll have left over in that lower transformed form, and then you just go backwards, back substitute. So at the beginning, you could start the same way as we did with the cubic or the quartic, depress it so that we get rid of this x to the 4 term. However, you can get straight away to one that removes both the x to the 4 and x cubed term all in one transformation. So basically, if you want, you can just skip that. And this transformation is called a Turnhouse transformation, which is basically a more general polynomial transformation, similar to the ones that we saw for solving the cubic and the quartic, except those were linear for, depressing the equations. This one will have some higher order ones. And now with these ones, when they're higher order, other than just, substituting in the new equation and then expanding everything out and then back substituting at the end, this one with higher degrees, it's done by this thing called taking the resultant of two polynomials, basically the one that you have and the transformation. Now I could show the formula here, a very large determinant, a Sylvester determinant, that can help you get it. At least there's that formula, right? There is some pattern to get the coefficients in the right place and whatever like that. You could also use, I think, what's called Newton polynomials or Newton's identities. But yeah, it's not as pretty as the substitution or the transformation from the previous videos. But, it's there. You can do it. Usually I would always do this on the computer. So I'm just going to say, so we're going to transform it with y is equal to a quadratic one, x squared plus mx plus n, and we're going to find these m and n coefficients afterwards. Notice that I also highlighted this is equation 1, and we're going to call this equation 2. There's going to be multiple equations. We're going to have basically f of y, so the transformation, which is going to be in terms of y, to be equal to 0, where we have that f of y is equal to the resultant of equation 1 and 2. Basically from 2, it's just like y minus the right side. That's what you're going to take to plug in over here. Then you compute the super long determinant, and you're going to get a new Quintic equation plus b1 y to the 4 plus b2 y cubed plus b3 y squared plus b4y, and then plus b5 is equal to 0. Now this transformed version, you basically have an expression between the coefficients of both polynomials, and this one equals 0 if and only if they both have a common root. So that's basically where we get the transformation and how you can back substitute like that. Now that we have this transformed quintic here, what we're going to want to do is solve for m and n from setting b1 and b2 to be equal to 0, right? This is what we want to do. We want to make these disappear, and we'll get the principal quintic form, which only has the y to the 5 and then squared and lower order terms. So I'm going to solve for m and n from setting b1 to be equal to 0 and b2 to be equal to 0. Now this is basically it's going to be like a system of polynomial equations. Okay, over here it only gets up to solving a quadratic, which we know the formula for that. Basically these transformations we're going to take such that we can, transform and also back substitute afterwards using all the previous formulas from like quartic, cubic, and lower down, so that it is going to be solvable with what we already know. So yeah, we're going to apply this. Again, you only have to solve at most a quadratic at this step, and we're going to get y to the 5 plus uy squared plus vy plus w is equal to 0. This is our third equation here, the principal quintic form. Now we're going to use another transformation to get to the what's called Bring-Jerrard normal form, or Bring-Jerrard form, which is just this, but you only this squared term goes away, and you only have the power of 5, and then the linear terms. So now you might think, are we going to use a cubic transformation? Well, no, actually, we're going to use a quartic transformation. And you might think, well, why would we use a quartic one if we want to eliminate basically three terms instead of 4? And we're going to see that if you try to use a cubic one, at least as far as I know, you're going to have to solve a sextic, which we can't do. And we're going to use this extra fourth term or fourth coefficient from this quartic substitution to make it so that we only have to solve at most a quartic, or at the end we're going to see it's going to be a cubic, and we already know those formulas, so it's going to work. Sorry, this has to be in z here. We're going to use the transformation z is equal to y to the 4 plus py cubed plus qy squared plus ry plus s. And we're going to get an f of z is equal to 0, where we know that f of z is equal to the resultant of, this is equation 4, the resultant of 3 and 4. Okay, so you compute again the super long determinant, and we're going to get a new quintic in z to the 5 plus c1 z to the 4 plus c2 z cubed plus c3 z squared plus c4 z plus c5 is equal to 0. Now, for the solving part for the coefficients, what we're going to want to do, we're going to solve for P, Q, R, and S from this set of equations. It's going to be, again, the first three except the leading term set equal to 0. So C1 is equal to 0, C2 is equal to 0, C3 is equal to 0, and then one more embedded coefficient, which we'll call E1 to be equal to 0, which basically over here, E1 E1 is R's coefficient from C2, okay? This one over here, you're going to find that from solving this one, E1 is equal to 0, that you're going to essentially, I believe, eliminate R, and then you're going to have a free variable, and you can use that extra one to also solve C3 is equal to 0, right, along with the other ones. But that allows you to get this term also basically canceled out, and you don't have to go above all the other formulas that we would have seen before already. So it's going to be solvable that way. Now, after you do this, you finally get into the Bring-Jerrard form, which is going to be z to the 5 plus az plus b, okay, is equal to 0. Now we're almost done here, or at least for the transformation, right, not the actual method. So we're going to use just the simple substitution. U is equal to z times a to the minus 1 over 4. Okay, and basically here, all we're going to end up with, we're going to end up with u to the 5 plus u plus capital A is equal to 0. So now we just have this one with no extra coefficients here. You have 1 in the front here, 1 in the front, and then this extra term here where the capital A is b times a to the minus 5 over 4. So now with this, now you have to know a certain series solution method here for inverse functions. It's called the Lagrange inversion theorem or Lagrange reversion theorem. Some people, they say they're essentially equivalent, but some they would essentially distinctify or differentiate one from the other, as in Lagrange inversion is for reversion of series, while Lagrange reversion theorem is for reversion of implicit equations, which here that's basically what we're going to have when we rewrite it. So I'll just show the main formula here on the page, on the screen. Basically, you would just transform it like that. We got to rewrite it in the proper form. We're going to have u is equal to minus a minus u to the 5, right? And now we're going to get the solution by using, we're going to use Lagrange reversion with, we're going to use it with basically the phi function, phi of u, to be equal to u to the 5 and f of u to be equal to u, so the identity here. And so what we're going to get here is what's known as the Bring radical, which is again basically like this extension of a radical for this reduced Quintic equation for one of the solutions, right? So we're going to get that using this formula, u is equal to, the Bring radical is also sometimes known as BR, like this, but it's basically going to be, so we have the minus a here, and then we're going to get minus a plus the sum as k is equal from 1 to infinity of minus 1 to the k over k factorial, and then times the k minus 1th derivative with respect to u of u to the 5k, right? Basically this function here to the k, and this is evaluated at the point minus a. U is equal to minus a. All right, now for the nth derivative of a power function, it's rather simple to do. You'll see that just you have cascading powers Obviously, when the exponent of the function n and the order of the derivative are equal, like if they're both, then you're going to get n factorial. But otherwise, it's not going to cancel all the way to be just a constant, and you're going to have this cutoff factorial, which is basically the falling factorial. And you can rewrite this in a certain way like this. So we're going to have the minus a plus the sum is k is equal from 1 to infinity of minus 1 to the k times, we're going to have 5k factorial divided by k factorial times 4k plus 1 factorial, and from the remaining minus 1 power here, we're going to have minus 1 to the 4k plus 1, and then a to the 4k plus 1. Okay, this is what we have now. We basically rewrote the falling factorial in terms of normal factorials. Now we can rewrite this factorial expression in terms of the binomial coefficient. So we're going to have minus a plus the sum k is equal from 1 to infinity of 5k, choose k, minus 1, the k plus 1, or minus 1, right? It doesn't matter if you add or subtract 1 for this, times a to the 4k plus 1 all over 4k plus 1. And now you will also notice that basically you can this minus a over here, the initial term, is also absorbed into the same nth term, so we can rewrite it from k is equal to 0. Also, I'm gonna factor that out so that we start from inside the series at least an initial term of 1. So we're basically going to have minus a times k, the series k is equal to 0 to infinity of 5k, choose k, times minus 1 to the k, a to the 4k over 4k plus 1. Okay, so this is what we have now. You can also find with the ratio test that you'll find that this converges for absolute value of a is less than or equal to the 4th root of 3125, right? This is a little bit less than 1, I believe. But yeah, that's actually quite a small window. And what we actually do is we take the analytic continuation of this for all a so that we get a complete solution, right? It's not going to be bounded to specific values of a. Now, with this, what we can do is we can rewrite it as a generalized hypergeometric function. Now, a hypergeometric function, if you haven't heard of these, you could, again, look it up on Wikipedia or something like that. But basically, these are like the biggest class of special functions that just appears everywhere. Everything can be rewritten in terms of them and this sort of thing. And they're characterized by this certain rational ratio of consecutive terms. And basically, we can use that, as shown on screen here, to transform it into a hypergeometric function and use its analytic continuation. And so again, you just check that ratio, we get what we need, and so this is going to be able to be rewritten as minus a times the hypergeometric function for f3, right? That means we're going to have basically 4 rising factorials on top, and 3 on the bottom of 1 over 5, 2 over 5, 3 over 5, 4 over 5, and we have 1 over 2, 3 over 4, and 5 over 4. And then the main argument over here is minus 3125 a to the 4 divided by 256. Okay. So, and this works for all a's with its analytic continuation. And this is actually the first solution. However, how are we going to find the rest of them? So, in order to get all 5 solutions, or basically the remaining 4 here that are missing, what we're going to have to consider is a slight rearrangement or rewriting of the bring quintic here at the end. So what we're going to have is, again, u to the 5 plus u plus a is equal to 0, the bring quintic. We're going to move it to the side so that we're going to have u to the 5 is equal to minus u minus a. And now what we're going to do is we're going to divide by u. So we're going to have u to the 4 is equal to minus 1 minus a over u. Now, just notice here that the fact that we have this 1, again, excluding the minuses here, the fact that we have this 1 in front as the coefficients is not the only thing that we actually could have here. To get 4 other solutions, we can use the quartic roots of unity, 1i minus 1 and minus I, because all of those to the power of 4 also equal 1. So for each of them, we're going to have minus omega to the 4 minus omega to the 4 a over u, right? Where again we have that this is basically an element of 1 minus 1 I and minus I, right? This is what we have. And so now we can expand this now as a power series solution, again using the Lagrange reversion theorem. Now we have a composed function basically, or a function of u, and we want to get the individual u. First we're going to let v to be equal to u to the 4 so we can rewrite this in a clearer way, and what we're going to get is v is equal to minus omega to the 4 minus omega to the 4 a divided by v to the 1 over 4, right? So now we can use Lagrange reversion theorem with phi of v to be equal to 1 over v to the 1 over 4, and f of v to be equal to v to the 1 over 4. Alright, so now we get all of the other solutions, u, 2, 3, 4, 5, as v to the 1 over 4, which is going to be equal to minus 1 to the 1 over 4 times omega plus, and then we're going to have the sum k is equal from 1 to infinity of minus 1 to the k omega to the 4k times ak divided by k factorial, and we have d to the k minus 1, the k minus 1th derivative with respect to v of this thing 1 over 4v to the k plus 3 over 4. You're just going to have to rewrite this from the substitution, and it is at v is equal to, again, this is basically minus 1. It's just minus omega to the 4. That's what we're going to have here, okay? So now, all you got to do is just expand and rewrite this. So we're going to have minus 1 to the 1 over 4. And when I talk about this, I mean the principal solution over here of the fourth root, right? That's why we have power 1 at the top. Times omega minus, you can factor out a 1 over 4 here. We'll have the sum. K is equal from 1 to infinity of, let's rewrite from the denominator here first. We're going to have k factorial there minus omega to the 4 times, or to the power of 5k minus 1 over 4. And then on top of the numerator is omega, right, to the 4k times a to the k, and then times this gamma functions remaining. Again, here we basically would have fractions. Again, you can convert the factorials to gamma functions. If you don't know about the gamma function, you can see my gamma function video extending the factorial. We're going to have gamma of 5k minus 1 over 4 divided by gamma of k plus 3 over 4, okay? And then once again, this one is also going to be able to be collected, so we have minus 1 over 4, and start the series from k is equal to 0 to infinity of, a little bit more rewriting here, minus 1 to the 1 minus 5k over 4 times omega to the 1 minus k a to the k. Denominator here is just k factorial. And once again, we have the gamma functions, 5k minus 1 over 4, and gamma of k plus 3 over 4. And again, you'll find that using the ratio test, it converges for the same thing, 4 over the fourth root of 3125. But now, I don't actually know how to fully do this. I just saw this on the article here, but essentially you can use Gauss's multiplication theorem, which is basically the formula for like the gamma function of n times z. That one, which I didn't really cover in depth in my video, but it's just the extension of the duplication formula. You can apparently use that to express this and split it up as a finite sum of hypergeometric functions. Now, I could not figure out how to properly do that. If anybody knows in the comments, they could share that. But basically, I'll just write what the result will be in the end. And again, with rewriting as hypergeometric functions, we can use their analytic continuation, so we don't have to, you know, fix this to one specific a value. So what we're going to get in the end, I'm just going to scroll here and just speed this up since it's a lot of them. Alright, so finally, God, my fingers hurt. I also am kind of slow anyway. I was trying to make it a little bit more clear. But there you go. We basically have this sum of 4 different 4f3 hypergeometric functions. And then again, there's 4 solutions, one for each quartic root of unity. And then overall, added with the initial one, we have this complete analytic solution to the Bring-Jerrard Quintic. Now, all you have to do is back substitute stuff. However, as you may have realized, given that we had transformations that were higher than degree 1, we had degree 2 and degree 4, we're going to get different solutions for different solutions within back substituting that we choose for the final answer. Now the thing is that you have to choose the right one. Some of them, they just give extraneous solutions. So even then, at that point, you already have to like do some numerical solving anyways. So it's kind of pointless to do it analytically, except again as sort of a proof of concept. And literally, I found nowhere on the internet anyways that ever showed it in full back substituted form with no extra substituted expressions, right? So yeah, it really is the most annoying thing in the world to do. And theoretically, this type of substitution or transformation series that we did here could also be used to further degree polynomials. I don't know if there's one for a sextic that makes it work, but maybe at least this one here, it works well enough. And actually this pattern using the hypergeometric functions at the end can also be applied to a more generic trinomial of like u to the k plus a u to the l plus b, where you have k larger than l, and you're going to have the same thing where you have the total k solutions. You're going to have a principal one, and then you're going to divide out by the l, and then you're going to get those with the lth roots of unity, right, basically. So that's a thing that carries over. And this solution here with hypergeometric functions is also rather close to another method which uses what's called differential resolvents. I have some resources in the description if you want to look into that, but basically you take the Bring-Jerrard Quintic at the end and you repeatedly implicitly differentiate to get basically like a function u of t over there, and you want to solve that so that you can solve the original Quintic, right? And again, there's a thing where you get like a principal solution from the series, and then you get 4 independent solutions. You can show that it's of hypergeometric type, except that takes a ton of expanding. Again, there's no way to really avoid the huge amount and torture of work to get to the full solution. And then again, that kind of works hand in hand with the way that you can generalize this to higher degree trinomials. There's also a way that you may see mentioned on the internet using elliptic functions, which is basically sort of the same way as solving the like cubic, for example, using trigonometry, where you have a trigonometric equation that you try and link it to, and this one we have an elliptic or modular equation that you link it to, which is of degree 6. And so that's sort of nice if you know elliptic functions. There's so much to know within the background of that, and elliptic integrals, Jacobi theta functions, all that kind of thing. I guess it provides maybe a more systematic way at the end of it, but I already think that the way we did it here with hypergeometric functions is pretty good enough. And yeah, if you want to, if you're comfortable or something, you could go learn into that. That's the original one that I was looking at, because a lot of people were that's the main type of solution that they may have heard or has been passed around. So anyways, yeah, I have further reading if you want in the description, but please, I pray that you don't actually use this in full form, especially not on paper. Even then, I don't know if you'll have to wait like a week or something, or use like a supercomputer to get the symbolic coefficients to evaluate for the full solution. it is really not worth it. I just covered it because, well, I figured out one way that it sort of makes sense how it works. It's just don't do the heavy lifting, don't do the heavy work for this. So I hope you enjoyed this video. I don't know if I'm going to do any other stuff with this in the future. This is probably it. And yeah, like and subscribe. I will see you in the next video. Goodbye.